It doesn't work. No batteries. Okay, can you hear me?
Yes.
Thanks.
Yes.
Okay, thank you. Now you should also be able to see the slides. Full screen. Okay. Okay. Today, okay. Let me record the class. Okay. Basically, today I'm going to show you the remaining rule for computing derivatives of two variable functions, with with one example also with multivariable functions. But I will focus mainly on the composite function and the chain rule, by reviewing briefly the chain rule for one variable functions, and then showing you examples for two variable functions, in particular the log derivatives of two variable functions. Okay, so basically there is almost nothing new conceptually, but there are more cases that at least I believe are really important and found very often in the basic models, okay? The basic techniques to deal with two variable functions. Okay, so what is the chain rule? The chain rule is the rule for computing the derivative of a composite function. A composite function means a function of a function. The concept of composite function is something, is a structure that we may have in our mind. We look at a function as a composite function. And usually there are different ways, there may be different ways to look at the function as a composite function. Okay, different possible structures. It depends on what we have to do with that function. Okay, so we must select sometimes the most convenient way to look at the function as a composite function. Okay, but basically it is a very useful structure to compute derivatives in a convenient way. So what is, for one variable functions, the structure of a composite function is like this. I have a function g of x, okay? And the dependent variable is called u. On its turn, the dependent variable takes one value corresponding to some particular value of x. It becomes the input of a new function, h, and h transforms u into y. So basically, we have a process by which x is mapped into y in two steps. Of course, if you look at the textbooks and the definition of composite functions, you can see certain formal statements, for instance, that h must be defined at least in a subset of the range of g, which is quite obvious, okay? Because, for instance, suppose that g, you put the input x, g transforms the input into something which is negative, and then h is the log of something. It doesn't work in this way because the log of a negative number doesn't exist, okay? So this is the meaning. H must be defined at least in a subset of the range of G, okay? Then we replace here U with G of X, and we have that Y is H of G of X, okay? or for short, y is equal to f of x, where f is h, is the composition between h and g. This is the symbol to denote the composition. G is the inner function and h is the outer function. It is convenient to regard y as a function f, which is the composition between a and g. And the basic theorem on the derivative of composite functions states that if g and h are differentiable, which means they have their derivatives over their domains, then their composition f is differentiable as well. So it's possible to compute the derivative of the composite function. Okay, and the derivative of the composite function, dy over dx, is the derivative of y with respect to u, okay, y with respect to u, times the derivative of u with respect to x. So it's a chain, it's a product between two different derivatives. Okay? The derivative of the inner function with respect to x times the derivative of the outer function with respect to the image of x. Next, we don't want to follow literally this step when we compute these derivatives. Particularly, we want to have the result immediately in terms of x, not in terms of u. But just remember that u is g of x. Okay, so you can write this in this way. This is another way to state f prime of x is h prime of u times g prime of x. But u is g of x. So just replace g of x here instead of u, and you have h prime of g of x times g prime of x. This is the rule for the derivative of a composite function. Now I'm going to show a few examples with one variable, next a few examples with two variables. Probably one of the most important differentiation rules in applied mathematics applied to economics is the rule for the log derivative of a function. The log derivative is the way the derivative of the log of a function is called. Okay, the derivative of the log of a function is called the log derivative of a function. Okay, this is clearly the derivative of a composite function. It is not the derivative of a function, it is the derivative of the log of a function. Okay, this is really important. That will be a particular case that we will see in a moment. Okay, so this is the first conceptual framework for the chain rule. This is an example with one variable. Of course, this is just the first example. So I show you all the intermediate steps, but we don't need to change the variable to call x squared plus 1u, okay, and then work with two different functions and two different variables. We can do that in one step later, in blue here. But of course, if you have this function, the cubic root of x squared plus 1, the cubic root of x squared plus 1 can be regarded, this is not the only way actually, can be regarded as a composite function. Because the argument of the cubic root is x squared plus 1, I can regard it as g of x. And I can call it u. Then everything reduces to to computing h of u, which is u to the power 1/3. Of course, this is not the only way, because one could even imagine three different steps. Okay, the first function is x squared. The second function is add 1. Okay, x squared plus 1, and then the outer function is a cubic root of this variable. Of course, this is a simple case that we don't need to make it in 3 steps. 2 steps are enough, but there are some functions have a complicated structure, so an outer function, then an inner function, but the variables in this inner function are functions of x through some other function. So in some cases we need to repeat the chain rule 3 times, 4 times, and every time we have a product here, okay? Between all the levels, the derivatives at all the levels of the function. Okay, so if I want to apply literally the rule, the derivative of g, the derivative of u with respect to x is 2x, okay? 2x. And the derivative of y with respect to u, it's the cubic root of u, it's 1/3 times u to the power of minus 2/3. So this is already the final derivative, the final result, provided that here we replace u with x squared plus 1. So we can replace here u with x squared plus 1, and we get this one. So, okay. So this is basically what we do, okay? So the derivative is 1/3 u to the power of minus 2/3, and this is the derivative of h with respect to u times the derivative of u with respect to x times 2x. Then we replace here x squared plus 1 to u, and we have the final expression of the derivative. Is that clear? We don't do that in general, at least for these simple structures. What we do is this. Basically, we take this one. We regard this one as a function of the whole argument of the root, and we know that the power function as a derivative, the cubic root of something is 1/3 times something to the power of minus 2/3, okay? And we write this. Then we compute the derivative of something, which is inside the root, with respect to x. So this is what we do, without all these intermediate steps. And we get the final result, of course, the same result. Of course, then we can take basically the basic differentiation rules and imagine that there is f of x instead of x, and then we can obtain the differentiation rules for these composite functions. For instance, you know the differentiation rule for the power function, the elementary power function, which is, this is an example already, okay? Which is x to the power of alpha as its derivative alpha times x to the power of alpha minus 1, okay? If instead of having x, I have the power of an f of x, the rule is the same, it's alpha times f of x to the power of alpha minus 1, but since this is a composite function, I have to multiply by the derivative of f, which is the base of my power. So f prime of x times f prime of x. There are some very important particular cases. One is 1 over f of x, which is the reciprocal of a function. And the reciprocal of a function can be regarded as a power function with exponent minus 1, alpha is equal to minus 1. So y prime, which is another short notation for the derivative, is minus 1 times f of x to the power of minus 2 times f prime of x, equal to minus f prime of x over f of x squared. That clear? Okay. So these are two examples with one variable. Do you feel, I mean, is that clear for one variable function? Because now I'm switching to two variable functions, okay? Okay. So, for instance, if my function is f of xy is some function h, not of g of x, but of g of xy. Now look at the structure here. in one variable case, this may not be obvious in general, but I'm going to show you something really important here. Just relax and try to follow what to listen to what I'm saying now, because I want you to focus on structure more than difficult computations. It's more important that you focus on structures and you a one variable composite function. I have f of x Why is that? Not really good. Oh my God. Okay, doesn't work. No problem. Everything is already there. So I'm just describing. Moment, please. I will change my pen later. No. No, it doesn't work. Okay, no problem. Just look at this idea, because today we have everything already here, but in the case of one variable function, I have a simple, there is only one possible structure of composite function, which is this one, okay? A one variable function of x and a one variable function of u. But in the case of two variables, I'm going to present now a particular structure, which is very common, but there are more structures. For instance, we may have here I have the inner function, which is a two-variable function. But what about the outer function in this example? This is a one-variable function. This means that in the first step, I have two input variables, x and y. In the first step, I have g that transforms the pair xy into a number. And then this number is again transformed by a one-variable function, h. This is one possible structure, but there are more. For instance, here I could have another two-variable function. I could have h of two inputs, g of xy, a two-variable function, so this is a number, g of xy, and then another input that could be m of xy, okay? So I have xy, put xy as an input into my box. There is one function g that transforms xy into a number, and this is the first variable that will be the first variable for the outer function. There is another function m of xy that transforms xy into another number. So this would be a function of two variables, okay? H would be a function of two variables. There are more structures, and one is particularly important. H, I have, for instance, a function, don't look at H, look at G of xy, where both, and this is a two-variable function, and both x and y depend themselves on a unique variable. So both x and y are themselves functions of one variable. For one typical example is when I have x, which is x of t. This is a variable that changes over time. It's a function of time. Y is y of t, another variable that changes over time. At a given point in time, I have a given value for x and a given value for y, put them into g, and I obtain the result, g of xy. But this is, in fact, a function of one variable. So the result is a function of time. It's a one variable function. So with multivariable functions, we may have many different structures for the chain rule. This is one very common. So the inner function is a two variable function or an n variable functions, and the outer function is a one variable function. This is a common structure. So what about the derivative with respect to x of g of xy squared? So imagine that I have a function of two variables, the square of this, and I want to take the derivative of this with respect to x. Okay, so this is a power function of a two variable function. The exponent is 2. So the derivative is 2 times g of xy times what? I apply the chain rule, the derivative of g with respect to x. Because don't worry about the partial derivatives, they are derivatives of, in principle, of a one variable functions, because the other variable is fixed at a given level, okay? So this is, in fact, I regard this as a function of x. So it is 2 times g to the power of 1 times the derivative of the inner function with respect to x. What about the derivative with respect to y of this g of xy squared? It is 2 g of xy times the derivative of g with respect to y. Here is another example. The derivative with respect to x of the square root of x plus 1/2 y squared. Okay, take the derivative of the square root with respect to its argument. Okay, I want to compute the derivative with respect to x here. Derivative of the square root with respect to its argument is 1 over 2 square root of. So I write this in this way, times the derivative of the argument of the square root with respect to x, which is 1. Okay? So this is the result for this one, and the derivative with respect to y is the first factor in the derivative is exactly the same. Why? Because I'm just taking the derivative of the outer function with respect to its whole argument, okay? So the first factor is the same, but now I have to multiply by the derivative of the argument with respect to y, which is 1/2 times 2y, it is y. Clear? Okay. Just if you are interested, I explained some of this stuff already, but I just want to briefly review it. It's in the slides. When dealing with elementary one variable functions, we focused on the natural exponential function. Y is equal to e to the power of x. And we know that for this function we have the derivative which is equal to the function itself. Y prime is equal to e to the power of x. More generally, if we have an exponential function of this type, a positive real number, positive base, a to the power of x, y prime is again a to the power of x times the log of a. Just remember this, this is an exponential function. Don't make confusion between this one and the power function. Both are powers, but in the exponential function, the variable, the independent variable, is at the exponent. In the power function, the independent variable is the base of the power, okay? And as a particular case of this, of course, when a, the base, is in particular equal to e, the log of e is 1, and we get, again, the rule for the natural exponential function. For instance, for the 2 of x exponential function, 2 to the power of x exponential function, I have that the derivative is 2 to the power of x log of 2, where this log is the natural log. The base of this log is e. Again, if we have the exponential function times a constant, capital A times e to the power of x, the derivative is equal to the function. itself. Okay, so these are the two cases in which two cases of functions of one variable having the derivative exactly equal to the function. Basically, the only case of a one variable function having the derivative equal to the function is this one. Okay? The function is a constant times e to the power of x. Is there any other case that you can imagine of a function having the derivative equal to the function itself? Identically means for any x. I would say there is one very trivial function, which is f of x equal to 0 constant. If a function is equal to 0, the derivative is 0. But of course, just I want to point out that this is included in this case, okay? Because in this case, we have any real number a, any, can be 0 in particular, and if it is 0, then the derivative is included in this case, okay? So this is the only case of a one variable function having the derivative equal to itself. And there are some problems that will be part of the second part of this course that are called differential equations. Differential equations are equations in which the unknown is not a number, like for the quadratic equation of basic algebra, okay, high school algebra. The unknown is a function. So we may find this differential equation. This is one of the most elementary cases. Find all the functions such that the derivative is equal to the function itself for any x of the domain, okay? And there are techniques to solve these equations. The solution is a function or a family of functions that satisfies the differential equation, okay? So this is just to link this with the next part of the course. Another example here is capital A times the exponential of alpha x, where alpha is a real number. And if you compute the derivative here, you know that the derivative is capital A times the exponential of alpha x times alpha. So in this case, the derivative is not exactly equal to the function, but it is proportional to the function through a coefficient of proportionality alpha. This is another example of differential equations, okay? So we may find this one. In fact, this will be the first one that we will find, and we will learn how to solve differential equations using one for which we already know the solution, okay? We will learn the techniques to solve differential equations starting from this one. Okay, so this is another differential equation. Find all the functions such that the derivative is proportional to the function itself. Here are examples. And you may remember from the elementary function, the first class on elementary functions, that these kind of functions have a constant growth rate, okay? So y prime over y, which means f prime of x over f of x, is equal to alpha. And this is called the constant rate of growth, which is different from the rate of change, okay? So the rate of change is the derivative, the rate of growth is the ratio between the derivative and the level of the function, and this quantity is also called the log derivative, logarithmic derivative of a function. So what about an exponential function in which we have not the exponential of x, but the exponential of a function of x? Just regard it as a composite function. For instance, 3 times exponential of 2x squared minus x. Its derivative is again 3 times the exponential of 2x squared minus x times the derivative of the exponent with respect to x, which is 4x minus 1, okay? This part of the slide is, I mean, if you are curious about this, just have a look at this. This is about the derivative of the logarithmic function. We know that the logarithm y equal to log of x, natural logarithm, has as its derivative 1 over x, okay? 1 over x. If you are interested, just look at these two lines. The rule for the logarithm, for taking the derivative of the log, can be obtained starting from the rule, the derivative of the exponential function, and the rule, the chain rule, basically. Why? Because I can regard the log of x as the inverse function of y equal to exponential of x. Okay? What is the meaning of inverse function? The definition, if I have a function of one variable, I can define the inverse function, this, and the inverse function of a function has this property. If I make the composition between the inverse function and the function itself, I get, as the composite function, I get the identity function. Okay? This means that the composition of one function and its inverse is the identity function. The identity function is f of x equal to x. Okay? In fact, if you, for instance, take the log of the exponential of x, what do you obtain? X. If you take the exponential of the log of x, you obtain x. This means that the composition of these two functions is x. And using the chain rule and the derivative that we already know of the exponential function, we can obtain the derivative of the log. Okay, so this is not important. Just if you are curious, have a look at it, because it's quite instructive on using the composite function. Anyway, what is important to me is that you know the rule for computing the derivative of the log, which is derivative of the log of x is 1 over x. Okay. Next, the logarithmic derivative for one variable function. What is the derivative of the log of f of x? The derivative of the log of f of x is the derivative of a very special composite function, which is the log of a function. Okay. And I can use the chain rule. Take the derivative of the log with respect to its argument, which is 1 over f of x. Then multiply by f prime of x. So the ratio between the derivative of the function f and the function f itself is the derivative of the log of f of x, which represents the rate of growth of f of x at the local rate of growth of f of x at the point x of the domain. Okay? It's called rate of growth or relative rate of change. Okay? Remember, rate of change is the derivative. Relative rate of change. Relative means that I'm taking the ratio with the level already reached by the function. Relative rate of change or rate of growth is the log derivative. It's immediate to extend this to two variable functions. For instance, okay. For instance, here is an example with a one variable function. If I have the log, this is quite instructive because let me show this first. This is an example with a one variable function. If I have y equal to the log of the square root of 2x minus 1, of course, provided that x is larger than 1/2. Because otherwise, you cannot compute the square root. And if in particular x is equal to 1/2, then we have 0 here, but the log of 0 doesn't exist. So the domain is values of x strictly larger than 1/2. Compute the derivative of this function, which means the log derivatives of the square root of 2x minus 1. It's 1 over the square root of 2x minus 1 times the derivative of the square root of 2x minus 1. Okay? Here. What is the derivative of the square root of 2x minus 1 is 1 over 2 times square root of 2x minus 1, and then times the derivative of the argument of the square root, which is 2. So actually here we are taking the derivative in 3 steps. First step, derivative of the log with respect to its argument. Second step, this one, derivative of the square root with respect to its argument. Third step, derivative of 2x minus 1 with respect to x. Can you see the 3 steps? Okay. Now simplify everything. 2 and 2 disappear. Square root times square root of the same quantity is 2x minus 1. So the derivative has a very simple structure. It is 1 over 2x minus 1. Okay, so why is this the result so clear, so easy, despite the 3 steps that were needed to compute it? Because you could have started from a different expression for your function, which is 1/2 times the log of 2x minus 1, okay? Clear? Good. Okay, so this is the alternative way to compute this derivative. So the main message here is, before applying directly differentiation rules to functions that have quite complicated expressions, just try to simplify your function, okay? Power function of one variable. Next, there are examples with 2 variables, of course, but let me show you once more the case of 1 variable. Okay, power function of 1 variable is capital A times x to the power of r, where x is a positive variable, r can be any exponent, and a is a constant. Usually in applications it is positive, but it can also be negative. You know that the derivative y prime is capital A times r times x to the power of r minus 1. Then here I group the part of the derivative that corresponds exactly to the function, because x to the power of r minus 1 is x to the power of r over x. And then I can express the result as f prime of x is equal to r over x times f of x, okay? This is another very important way to write the result of the derivative of a power function. Now, compute the derivative not of this one, but of the log of this one. Well, this is the same f of x as before, but now we compute the derivative of the log of this, which is the log derivative of the power function. It's already there, because we know that the log derivative in general is f prime over f, okay? If you express the derivative in this way, you get immediately that the derivative of the log of a power function is f prime over f r over x, okay? This is why it's so important to remember this way to write the derivative of a power function. In this way, I'm writing the derivative of a power function. Okay, the full expression is this one. But if I look at the structure of the derivative, I see that the derivative of a power function is the function itself divided by the variable for which I'm taking the derivative times the exponent, okay? And this is a very useful expression, because in many cases we have to compute f prime over f, which is the log derivative, or the relative rate of change. And the relative rate of change is already there. It's r over x. So for a power function, the relative rate of change is not constant. For an exponential function, it is constant. For a power function, it is not constant. It depends also on x, the point at which I am computing this log derivative, okay? And in practice, what happens is that the larger x is, the smaller the rate of change. The relative rate of change is. The smaller the rate of growth is. If you're not sure about the result, this is the second convenient way to compute the log derivative. Remember that the log derivative, is the derivative of the log of a function. If the function has a multiplicative structure, don't use this rule, f prime over f. If the function has a multiplicative structure, my suggestion is don't use this rule, f prime over f, to compute the log derivative, but take logs first and then compute the derivative, okay? Because for a multiplicative structure, the log of the function, we have an additive structure, okay? And then you can compute the derivative of each term, and then add, take the sum of the derivatives in the result. For instance, what is the log of capital A times x to the power of r? It has a multiplicative structure, so it is the log of capital A plus the log of x to the power of r. So it is the log of capital A, which is a constant, plus r times the log of x, okay? Then, when computing the log derivative of the original function, I can compute the derivative of the log. The log is here. So the derivative of this one, this is a constant, it disappears, this becomes r times 1 over x, r over x, which is exactly the same result as above. There are many cases in which we have multiplicative structures. For instance, this power function could be multiplied by an exponential function, okay, or by another function, okay, which increases or reduces the value of the basic power function as a factor. In many applications, for instance, the exponential function could be related to discounting, okay? So this is some aggregate, and then you multiply by an exponential function that could represent reducing the value because the value of that quantity is related to some point in the future, okay? But you may have very often multiplicative structures, and you may want to compute the log derivative. So don't use f prime over f, take logs first, and then compute the derivative, which is more convenient in general, okay? Okay, here are more examples with two variables. Some of them are already known to you because we started last time to compute this. But anyway, here is a summary of computations that are quite standard. Also in the simple optimization problems in two variables, etc., we very typically compute derivatives of these kind of functions. Okay? Suppose that your function z is the exponential of the square root of x plus 2y. What is the derivative of z with respect to y? First of all, this is an exponential, and the exponential is a one-variable function, but the argument is two-variable function. So I take the exponential of the square root of x plus 2y times the derivative of the exponent with respect to y. So times 1 over 2, again the square root of x plus 2y times 2. This is again in 3 steps, you see? Derivative of the exponential with respect to the exponent, but the exponent is a square root of, okay? Then the derivative of the square root with respect to its argument times the derivative of the argument of the square root with respect to x. 3 steps again. Then I can simplify something here, and this is the final expression for the result. Derivative with respect to y. The derivative with respect to x, basically nothing would change except that the last factor would be 1 here, okay? But the first 2 steps would be the same, because they are derivatives. So the two-variable function is just the inner function, okay? But the first 2 steps that refer to the 2 outer functions are the same. Okay, this is the standard, the power function in 2 variables, Cobb-Douglas function, where capital A is positive and the 2 exponents alpha and beta are positive as well. Okay, so the derivative of our function with respect to x. This is already an example we made last time, but useful to repeat it. This is the derivative with respect to x. Okay, I regard the function as a function of x. So y to the power of beta is like a multiplicative. It's like a multiplicative term. Okay, so capital A times alpha times x to the power of alpha minus 1 times y to the power of beta. Now I rewrote here x to the power of alpha minus 1 as x to the power of alpha divided by x. And I group together with this green area, in this green area, the part of the derivative which is exactly equal to the original function, okay? And this means that the result is alpha over x times the original two-variable function, capital F of x1. The same for y. You can do the same experiment. If you take the derivative with respect to y, then you have capital A times, now it is x to the power of alpha, which is a kind of multiplicative factor, like a number, x to the power of alpha times beta times y to the power of beta minus 1, which again can be written as y to the power of beta over y, okay? Then you have beta as an excess factor compared to the original function, and the result can be expressed as beta over y times capital F of xy. And these two expressions that relate each of the partial derivatives to the value, to the level of the function, are very useful to, one, to compute the logarithmic derivatives, two, to solve problems in which you have to take the derivative of this function, which is, they are problems of maximizing the output or maximizing the utility subject to a budget constraint, okay? Typically, we have a Lagrange function, we have to take the derivatives of this function plus something else with respect to x and to y, but if we write this in this way, then we have a common factor in both derivatives. It can be very easily cancelled, okay? And this is a very convenient way. Just keep this in mind. Otherwise, the computations become sometimes very tricky in some cases. So this is a really useful way to solve these problems. Now, suppose that I want to compute the log derivatives of this function. Not the derivatives of this power function in two variables, but the log derivatives. Okay, so my function is the same as above. I want to compute the log derivatives. They are denoted in this way. The partial derivative with respect to x of the log of f of xy, and the partial derivative with respect to y of the log of f of xy. Logarithmic derivatives. Okay, so the partial derivative with respect to x of the log of f of xy, which I denote by z, is what? It is, again, the derivative divided by the level of the function. But the derivative, of course, is the partial derivative with respect to some specified variable. So it is the derivative of f with respect to, partial derivative of f with respect to x over f. And the result is already there. It's here. Derivative with respect to x divided by the value of the function is alpha over x. Exactly as above for one variable functions. Clear? Alpha over x. Otherwise, you should put in the denominator this quantity, this one. In the denominator this quantity, and then simplify. But you would get alpha over x. So it's useful to keep in mind this structure already from the beginning. The partial derivative with respect to y of z, which is the log derivative with respect to y of f of xy, is the partial derivative of f with respect to y over the function. And it is similar, beta over y. So this is really also another useful insight. You have a two-variable function, power. If you compute the partial derivatives, look at the partial derivatives, they are both functions of the two variables again. But if you take the log derivatives, they are one variable functions. So in the log derivative with respect to x, there is no more dependence on y. Okay? In the partial derivative with respect to y, there is no more, partial log derivative with respect to y, there is no more dependence on x. Why is that? Because the dependence on x and y is in a multiplicative fashion. When you switch to logarithms of a multiplicative aggregate, let's say, you just take the sums, okay? So you will have sums of functions of x and functions of y, okay? When you take the derivative of this sum, depending on the variable you are taking the derivative to, the dependence on the other variable will disappear. Clear? So this is why the log derivatives do not depend anymore on two variables, but only on one variable. By exercise, you could, it's useful, compute the logarithmic derivatives, the same here, of this two variable function in the alternative way and more convenient way of taking logs first and then computing the derivatives of the logs. Okay? So take logs first. Okay, it's already here. Take logs first. What is the log of f of xy? It's the log of a plus alpha times the log of x plus beta times the log of y. Now, the logarithmic derivatives are just the derivatives of this new additive function, which is the log of the previous function. The log of a is a constant. Alpha log of x, if I take the derivative with respect to x, is alpha over x. Beta log of y, derivative is 0 with respect to x. Okay? This is why we get alpha over x. Similarly, the derivative with respect to y of this sum is 0 plus beta over y. Okay? So this is why we get this simplified, simple structures of the derivatives for functions that have a multiplicative structure. If we have a function with a multiplicative structure between different terms and different variables possibly, and we want to compute relative rates of change, okay, log derivatives, we have usually very simple structures. Okay, so this is basically what I wanted to show for the log derivatives of a two-variable function. Now, you may find this also in other. There are two sets of slides that I have uploaded, and there are some repetitions between these two sets of slides. But don't worry, I mean, it's there are repetitions, but of course, it may be because I focus on these structures many times over this course, okay, because they are really important. This is the last slides we saw yesterday. What about the case of a free variable function or an n variable function of power type? Nothing difficult. I'm so sorry that it doesn't work because I would like to add. So let me try again now. No, it doesn't work anymore. Sometimes this works. No, it doesn't work anymore, and I don't know why. Maybe the pen, maybe the battery of the pen, I don't know. Anyway, I will fix it by next week. Okay. I will fix it maybe during the break. Okay, so suppose that you have this one. F of x1, x2, x3. Now this is three variables. It could be n variables, okay? This is a power function in three variables. A times x1 to the power of alpha times x2 to the power of beta times x3 to the power of gamma. If I want to take the derivative, for instance, with respect to the second variable, x2, it's just the same structure as before. So the other variables x1 to the power of alpha, x3 to the power of gamma remain as constants, multiplicative factors. And what matters is capital A times beta, which is the exponent of x2, times x2 to the power of beta minus 1. The other factors remain the same. And this is again beta over x2 times the function, the original function of the three variables, okay? So this structure is much more general than in the case of one or two variable functions. The same for n variables. You can try with 4, for instance. Now, what are the elasticities of a two-variable function? Okay, let's consider the elasticities of a two-variable function. They are also called partial elasticities. You know what the elasticity of a one-variable function is. So what is the elasticity supposed to measure for a one-variable function? It's another measure of change, very popular in applied economics. Why it is popular? Because it measures the ratio between the relative or percentage changes of the dependent and independent variable, okay? So in many applications it can be useful to understand what happens to the demand of a given good if the price changes not by €1 or €2, but by 1%, okay? So it would be interesting to know whether the demand of that good changes, declines by 2% or by 0.5% or by 3% when the price increases by 1%, assuming to be in the standard case where the demand function of a good is decreasing with its price, okay? And this is an elasticity, very typically. The elasticity is expressed as a percentage, okay? It's expressed as a ratio between two percentage changes. For instance, the elasticity of -2 means that when the price increases by 1%, the dependent variable, which is the demand, declines by 2% compared to their values before the change, okay? So it's expressed as a number. And we say that the elasticities are pure numbers. So they do not depend on the units of measures, okay, of the two variables. So if the price is in euro and the quantity consumed is in kilograms, okay, you get -2%. But if the price is in dollars and the quantity consumed is in tons, you get again -2%. Okay? Is that clear? So it doesn't depend on the units of measure of the two variables. It's called a pure number or measureless. It's a pure number. So it's a very, very important indicator of the sensitivity of the dependent variable to the independent variable. Okay, so these elasticities of a two-variable function are called partial elasticities. Okay, if z is f of xy, what is the partial elasticities with respect to x? The partial elasticity with respect to x of my function is just the log derivative times x. Okay? So it is x times the log derivative of f of xy. So in order to compute elasticities, we need to compute log derivatives first. The partial elasticity with respect to y is, very similarly, y, the only thing that changes is y here, times the log derivative with respect to y. So we do the same, but with respect to y. So the log derivatives are also useful to compute partial elasticities of a two-variable function and also of the elasticities of a one-variable function. Clear? So keep these formulas in mind because they are very strictly related, closely related to the log derivatives. For instance, compute the elasticities of our power function, of our power function in two variables. Okay, so I don't want to repeat all the steps. I want to show you that also in this case we have two methods, of course, because they are closely related to the log derivatives. So we may just take ratios, or we may take logs first and then compute the derivatives. Okay, so this is our power function. Okay, the partial derivative with respect to x as this expression, you already know that. The partial derivative with respect to y as this expression. If I compute the partial elasticity with respect to f, I take the partial derivative times x divided by the value of the function. And the partial derivative, the log derivative is this one already, is alpha over x, but time x is alpha. So basically the partial elasticities of a power function are the exponent of the variable for which you're taking the derivative, okay? And they are constant. The partial elasticities are constants. They do not depend, this ratio between, this sensitivity measure, this ratio between relative changes for power functions does not depend on the particular level you start with, okay? They are constant. They do not depend on x and y. And this is why these power functions are called isoelastic functions. Isoelastic means having the same elasticity across the whole domain of the variables. Constant elasticity functions. Similarly, if you compute the elasticity with respect to y, you multiply y by the log derivative. We computed the log derivative in the previous step, p over y, beta over y, times y, this is beta. Okay, so the elasticities are already there, displayed as the exponents of the factors, the power factors of your power function. Okay. The second step, if you want to compute the elasticities, okay, this is a simple case. We already know the partial results, but if you want to compute the elasticities, you can also use logs, okay? Because the log of f of xy is, again, the log of a plus alpha times the log of x plus beta times the log of y. So, compute the derivative of this, it's just alpha over x multiplied by x, and you get alpha. And the same for the partial elasticities with respect to y. My suggestion is that in general, if you have a function of two variables and you want to compute the elasticities, and the function has a multiplicative structure, my suggestion is that you take logs first, and then you compute the derivative of the logs, and then you multiply by x or by y, depending on the elasticities that you want to compute. Okay? Okay, so is everything clear about measures of change for two variable functions, partial derivatives, log derivatives, partial log derivatives, partial elasticities? Okay. Now, before introducing the second derivatives, I want to focus more on these measures of change for multivariable functions. So I want to complete the part on applications of the first partial derivatives. before switching to second derivatives. Here are some examples of the differential. Okay. So you know what the differential of a one variable function is. I remember that we discussed the differential and the other measures of change for a one variable function, the differential, the log derivative, the elasticity. We discussed this already. Now we do the same for two variable functions. Okay? And the differential of a two variable function is also really, really important. And you have to, again, the numerical examples, the exercises will be very simple. Okay? Where is the difficult point? Difficult. The key point is having the structure in mind. So what is the differential of a two variable function? Okay? Not just the formula, what is, the meaning of the differential of a two variable function. So remember that when I want to compute, if I have a two variable function, so I have two variables. Now the two variables, since I want to be general, the two variables are called x1, which is previous x, and x2, which is the previous y, okay? Why? Because this is a more general notation. If I have four variables, I call them x1, x2, x3, x4, okay? Now, suppose that you have an initial point here, a1, a2. Corresponding to this initial point, you will have the value of your function f of a1, a2. So in the plane, I have the domain of my two variable function. If I remember when we discussed the change for a one variable function, I started from my axis and I took a change of the independent variable. But now we have two independent variables. And there are infinitely many possible directions where I can take a change of the two independent variables. For instance, I could leave A2 at the same initial level and take a change only in A1 by moving the point from this initial point A, this is written as a vector, A1, A2, A, underlined, by moving this here, okay? Or alternatively, I could leave A1 to the initial level and just take a change in A2, suppose a change in A2, just moving my point in the domain to this one. Is that clear? More generally, I can take a change in any possible direction here, any possible direction and of any possible size, here or here. For instance, if I move it this way, I reduce the second variable and I increase the first. If I do that, I reduce the first and I reduce also the second. If I do that, I reduce the first and I increase the second. In this particular case, I suppose I'm increasing both variables. A1 becomes A1 plus H1. A2 becomes A2 plus H2. There are two increments of the two independent variables. But then the new point in the domain is this one, A plus H, written with a vector notation. H is just an ordered list of two elements, H1 and H2. It collects the two increments. A, it collects the two initial coordinates, okay? A1 and A2. And the new point is denoted in X, which denotes a point in the plane, is X1, X2. So what is, okay, let me just start from this basic idea. So suppose that I leave A2 to the same level. I just change A1 to H1, to A1 plus H1. I'm just increasing a little the first variable. You know already what the differential is for a one variable function, okay? And you know the formula. is the product of the derivative at the initial point times the increment. Okay? And we could do the same here. The increment is h1 or delta x1. The derivative is what? It's the partial derivative with respect to which variable? X, because I'm supposing that y, the vertical variable x2, remains fixed at the level n2. I change only x1. I'm regarding this as a function of x1 only. But what is the differential in this case? It's the derivative, partial derivative with respect to x1 times h1. Okay? This would be the differential. The partial derivative of my function with respect to x1 at the initial point, computed at the initial point, times h1. That would be the differential in this case. If I assume instead that a1 is fixed, and x1 is fixed at the level a1, and I change only x2, I would have an increment h2 of variable x2. I would regard the function only as a function of x2, and I will measure the differential, which is the approximation of the change of my function, by multiplying the corresponding derivative at the initial point times the increment, okay? So that would be the partial derivative with respect to x2 at the initial point times the increment h2. This term would be the differential in this case. Okay? And what is this sum? This is due to the fact that I'm not changing only h1 or only x1 or only x2. I'm changing both. Okay? So, in the linear approximation, this is extremely easy. It's just the sum of the two increments that I would have by keeping alternatively the two variables fixed once at a time, okay? It's just the sum of the two partial increments. That clear? And the reason of this is that we are dealing with the linear approximation of our two variable function. Whatever our two variable function is, whatever the shape of our two variable function, okay? We are dealing with a linear approximation. A linear approximation is just the sum of linear increments, supposed increments of our function. So the differential of our two variable function y equal to f of x1, x2 is called this one, which is a linear approximation to its increment, to its true increment. This is the true increment of the function. We should compute the increment directly if we must know the expression of the function to compute the true increment, okay? But if we know that the two partial derivatives at the point, and we know what is the supposed increase of each of the variable, we can approximate the true increment through the differential, which is this quantity dy, which is just the sum of the two partial terms, okay? By increasing one variable and then the other variable. Because the change from this point to this one is the sum of two partial changes, of variable x1 and variable x2. So delta y is f of a plus h minus f of a. Okay, this is the true increment. It is approximated linearly by the differential, which is the sum of the two partial derivatives, each multiplied by the corresponding increment. So this is the differential of a two variable function. What would you expect for a 10 variable function? Okay? For 10 variable functions, we would have the differential given by the sum of the products of the 10 partial derivatives, each multiplied by the increment of the corresponding variable. That would be the same structure. So basically, when we use linear approximations, we can use a partial perspective and then take the sum. This is really important, of course, because it simplifies things a lot. Okay, so I will deal with some basic matrix notation and operations, including eigenvalues and eigenvectors in the second part, twice in this course. One is just to give you some basic notation, matrix notation for multivariable optimization. So in the first part of the course. And this would be very little, a few concepts, basically, a few structures, a few notations. And then little bit more details in the second part when dealing with matrix notation for dynamical systems. Anyway, I just introduced a few concepts. Okay, so this is a column vector with two components. This is another column vector with two components. This denotes the initial point because it has two coordinates, okay? This denotes the vector of the increments. If I want to model in a short way, short notation, the new point, it's enough that I write A plus H, which is the initial point plus the two increments, okay? Because the sum of two vectors is the sum element wise, okay? So the first element of the new vector is A1 plus H1. And the first element and the second element of the new vector is A2 plus H2. Okay? So I can take the sum of two vectors in the same order as the variables appear in the two terms that have to be added to one another. So this is the sum, the very basic property of the sum of two vectors. Just take the sum of the corresponding elements. And then there is another important vector notation because a two-variable function has two partial derivatives, okay? Usually, these two partial derivatives are put into a vector because they have an order, because the variables have an order, first variable, second variable. So I have the derivative with respect to x1, with respect to x2, to x3, to x4, etc. Usually they are put into a row vector, not column, row vector, which is called gradient. The gradient is basically the derivative of an n variable function. Since there are n derivatives, the derivative is not just a number, it's a vector. So the gradient of f at the point x equal to a is just the row vector of the n partial derivatives with respect to the n variables, like in this case. And also another thing that I already introduced is the short notation for the differential, because this is the reason why we model the gradient as a row vector and the vector of the increments as a column vector, because this is a basic case of multiplication between two vectors having the same dimension, means the same number of entries, one row and the other column, okay? And when I multiply a row vector like this by a column vector, multiplication is multiplication of the first element here times the first element of the second vector plus the second element here times the second element of the second vector. Okay, plus. So I take the sum of the result. But what I get here, if I model this as a multiplication between two vectors, is just the differential, because it's partial derivatives times its increment plus the other partial derivatives times its respective increment, okay? So this is the result of the multiplication. And this is very nice because I express the differential as the product, again, of a derivative times an increment, okay? But this is a vector of derivatives and this is a vector of increments. But the structure is preserved, okay? So in this way, also the notation is very similar to the one variable case. So keep it just, I mean, I guess it's very common to find this in application, this notation. I mean, you have to know what this means. Not really, I mean, being able to perform computations, but understanding immediately the notation is quite important. Okay, so this is an expression for the differential where h is the vector of the increments of the n variables, and this delta f is the gradient of the function at the point x equal to a. Just keep in mind that with this notation, the example here is with 2 variables, but we could have 10 variables, and the product has the same notation, okay? Because we would have 10 entries in the row vector and 10 entries in the column vector, and we multiply each entry by the corresponding one, and then take the sum, which would be the differential of a n variable function. Okay, so this is the notation for the differential of an n variable function at a given point a. Okay, so this is the vector with the n variables. At a given point, that would be a1, a2, an. We would have the row vector of the n partial derivatives, and we would multiply the gradient by the vector of the increments. Okay. Okay. Now, when we deal, just showing this, and next we will take a break. Okay. When we deal, I mean, is that clear? Is that too easy or too difficult? Just give me some feedback, also from home.
Pretty clear for me, thank you.
Okay, thanks. Just one answer. Is that clear? Is that too difficult to, I mean, is that stuff that you already know? Okay, very good. Okay, so what about the linear approximation of an n variable function near a point? Okay, this is strictly related to the differential. The only difference is notational. It's just a matter of notation, because in the differential, we have an initial point, okay, and we focus on the increment, okay? But instead of focusing on the increment, call the initial point, for instance, the coordinate on the horizontal axis, call it A1, and the new point, the new coordinate of the new point is x1. It's not a1 plus h1. Focus on the final level, not on the increment, okay? So basically, what is h1? It is x1 minus a1, okay? When we take the linear approximation, instead of focusing on the increment, we focus on the variable, okay? So h1 is x1 minus a1. It's the length of this segment, this difference. h2 is just x2 minus a2. Okay? And what is the differential? It's an approximation of f of a plus h minus f of a. But what is a plus h? It is the new point x. This is x1, x2, the new point, compared to the initial point a1, a2, which is fixed. So call this f of x, this f of a, and call the increments, respectively, x1 minus a1 and x2 minus a2. Repeat the formula for a differential, and you get the linear approximation. F of x can be approximated linearly by f of a. This one was in the first time before with the minus sign, because we focused on the increment of f. Now I move this to the right, plus the gradient at the point times the vector of the increments, but the vector of the increments is the vector of the differences between the new coordinates and the old coordinates of the point, written in terms of x. And this is a generic function, for instance, of two variables. This is a linear function of two variables, because this is a vector of numbers. So this is a number, This is a vector of two numbers, in the case of two variables, and this is a vector of two numbers. So what you get is a linear function in x1 and x2. A linear function of two variables is a plane in the three-dimensional space. So we are approximating our surface, it represents a function, with a tangent plane in the three-dimensional space. Okay? Now an example, an exercise of a linear approximation. Maybe we can just move the example to the next. We could take a break now, move the example to the next part, because the next part is based on numerical examples in which I would like to show you both a differential in one case and a numerical example in which we compute all the measures of change for a two-variable function. We compute the increment, the relative changes, and the elasticities, and whatever, both local and in terms of a finite interval. Okay. So I think we can switch. We can move this to the next part. Take a break now. We take a 15 minutes break now. Coffee break, and we start again in about 15 minutes. Again, we're going to start again. Please let me know if you can hear me and see me. Now I'm going to share my screen again. I hope I never stop the recording. Okay, that's good. And now there is an example, a kind of summary, which I guess you can also see the computations, very, you can realize the usefulness of these computations and linear approximations and the usefulness of these measures of change, okay, in two examples. One example is a simple two-variable functions, which is the log. You don't see the slides, or maybe because I didn't share them. Okay. Okay, wait a moment. Okay. Okay, now I'm sharing the slides, and you should see them. One is a simple function, which is the log of 1 plus alpha x1 plus beta x2. So it is the log of a linear function of x1 and x2. Usually these kind of functions are really, it's really useful to approximate them linearly because they are pretty flat. So when you take a linear approximation, you get very good approximations. Of course, in other cases, the linear approximation is not so good, but this is a useful example. And I assume alpha equal to 1/3, beta equal to 1/5, but you can also do that in general. Usually, with this type of functions, alpha and beta are positive parameters, and x1 and x2 are variables that can take positive values or non-negative values at least, okay? So 1 plus a variable, or 1 plus the sum of variables, is a function that if the variables are positive, the coefficients are positive, here you get something which is larger than 1, so the log is larger than 0. So they are very useful for applications 1 plus alpha x, or 1 plus alpha x beta plus beta y, okay? Also the log is positive. This is an increasing function in both variables, and you will see a concave function in both variables that starts at 0 and then increases to positive values. So it's very useful for applications. Alpha equal to 1/3, beta equal to 1/5. I want to approximate f of 0.15, 0.2 near a1, a2 equal to 0, 0. When I have to take a linear approximation, I have to specify the initial point. Because the linear approximation, you have a surface, you work with the tangent plane, not with the surface itself. So you have to specify the tangency point. Because if you take another initial point, you have another tangent plane, okay, to the surface. So you work with a different approximation. So I want to approximate this. A convenient starting point is 0, 0, okay, because these values of the variables are quite close to 0. So my initial point is 0, 0. Okay, so I compute the gradient. And then I evaluate the gradient at 0, 0. The gradient is the vector of the partial derivatives. Okay? So it is, remember, it's the log of a linear function. So it's 1 over multiplied by the particular coefficient related to the variable under observation. Okay, so the partial derivative with respect to x1 is alpha over 1 plus alpha x1 plus beta x2. The partial derivative with respect to x2 is beta over 1 plus alpha x1 plus beta x2. If I want to specify these values with my alpha and with my beta, alpha is 1/3, beta is 1/5, so I put the numbers here, and I have my partial derivatives here for my numerical example. What really matters now is to compute the partial derivative, so to evaluate the gradient at the point 0, 0. The gradient at the point 0, 0 has the numerator, and then the denominator is 1, because this is 0 and this is 0. So the gradient at the point 0, 0 is 1/3, 1/5. Okay? When I want to approximate the change, so this value of the function, this is an application of the differential, okay? I have an initial point, I have an increment. Remember that the initial point is 0, 0. The new point is 0.15, 0.2. In this simple case, the new point, the new coordinates are also the increments because they start from 0, 0, okay? So my A point, A1, A2 is 0, 0. This is H1, H2, but this is also the new points, okay? A1 plus H1, A2 plus H2, because the initial point is 0, 0. So the new coordinates correspond to the vector of the increments. This is a very common situation, approximating functions near point 0, 0. Okay, so the new value of the function is the initial value of the function. So what is f of 0, 0? F of 0, 0 is 0 here, 0 here. The log of 1 is 0. So f of 0, 0 is this one. Alternatively, you can move this 0 to the left and you have the differential here, okay? So the increment of the function. But this is 0, so the differential is equal to the value, the new value of the function, plus 1/3 multiplied by the corresponding increment, plus 1/5 multiplied by the corresponding increment, which is 0.09. Clear? Well, the true value of the function, or if you like, the true value of the increment, because the initial value is 0, this is a very simple case. The true value of the function, you can compute this by a pocket calculator, and this is the log of 1.09, 0.086. Okay, so this is the linear approximation, and this is the true value. The linear approximation slightly overestimates the true value for a simple reason, because this is a concave function. So a concave, I discussed yesterday concave functions for one variable, but it is exactly the same. They have a kind of shape like this. Remember, a concave function, you have a surface that represents a function, and all the points that lie below the surface are a convex set, okay? So it's like this. If you approximate this with a tangent plane, which is linear, and you use the plane to compute the values, you overestimate the values moving from a given initial point. That's quite intuitive, okay? So you overestimate the values. Okay, so now I just this is a numerical example for a specific increment, 0.15, 0.2, and specific numerical values for the new coordinates 0.15, 0.2. If you want to have something in general, if you want to write the equation of the tangent plane at the point, you have to replace this increment with, rewrite them as a variable x1 minus the initial level of the variable x1. Here, the variable x2 minus the initial level of the variable x2, okay? Now, it's not a number, it is a function. So this is the equation, basically, of the tangent plane at the point 0, 0. What I mean is that here we have a numerical example. Here we have a more general generator of numerical examples, in the sense that if the two increments, the two supposed increments, instead of being 0.15, 0 and 0.20, are 0.10 and 0.30, you can directly use the tangent plane here and compute them by putting here x1 which is equal to 0.10, and x2, which is equal to 0.30. Remember that in this case, it's a very simple expression for the tangent plane, because here with the two constants here are 0, okay? Now we will see another example in which we have to actually to switch from the increments to the variables, but there will be some initial point that is not 0, 0, okay? Is that clear? So it's really, I mean, it's really easy. It's a linear approximation, just a multiplication of partial derivatives times increments. And you can do that by looking at specific numerical increments, or in general, by expressing not the increment, but the generic value of the variable x1 and x2, and expressing the increment as x1 minus its initial level, x2 minus its initial level. But the partial derivatives that appear here are the same, of course, because they depend on the initial point of your approximation, the tangency point of your plane to the surface. Okay, this is another numerical example which is has a slightly more sensible interpretation in economic terms, because it is related to a power function in two variables, Cobb-Douglas functions. If you want to understand more about the quantities that we will obtain, just think of this function as a production function. This is a very typical production function. X is the amount of the first input factor, Y is the amount of the second input factor. A is a parameter that is assumed here 5. This is related to, let's say, to the technology, in the sense that the larger is A, the larger is the output for any given combination of the inputs, okay? So this is the level of the technology, basically. So A is equal to 5. Alpha here is supposed to be equal to 1/3 and beta to 1/2. Suppose an initial input level, 8 units of the first input factor, 4 units of the second input factor. We want to compute some measures of change. Okay, some measures of change can be computed. A way to compute them is to look at partial measures of change, partial derivatives, partial elasticities. So looking at what happens when I keep one input factor at the initial level and I change the quantity of the other, okay? Partial. There are also techniques to assume changes in both quantities, and approximating this. One is this one, differential, for instance, okay? Okay, suppose that x remains fixed at 8, but y changes from the initial level of 4 to the new level of 4.8. So this is a big change in percentage terms. It's a change of 20% of the initial level of input y, okay? Here? Okay. Exercise compute the true increment of the function, the difference quotient, the partial derivative with respect to y at the initial input level, the ratio between the percentage changes of the two factors, and the percentage changes of the output and the factor that changes, and the partial elasticities with respect to y of the function at the initial point, okay? This one and this one have the same nature. This one is discrete, this one is point measure, but you should expect that these two values are pretty similar to one another, comparable to one another, okay? And the difference quotient has the same nature as the partial derivative, okay? So you should expect that these two are basically similar to one another. They will change numerically, but the idea is the same behind these quantities, okay? Okay, so this is, just a matter of applying the rules that we already know. F of xy is 5 times x to the power 1/3 times y to the power 1/2. So f of 8, 4, the output level at the initial input combination is 5 times 8 to the power 1/3 is 2, y to the power 1/2 is 2 as well. So it's 20 units of output with this input combination, okay? Now, the true value of f, when I change only the amount of the second input factor, I can compute the true value by using the formula. It is 5 times x is again 8 to 1/3 is 2, times the square root of 4.8, okay? I have to compute it with a pocket calculator. It's 21.91. So the output changes by 1 almost 2 units, and we have basically a change of the output of about, I guess, 10%, okay? About 10%, 9 point something percent compared to the initial level. So this is an absolute change. Delta F is the absolute change of the output. It's measured in terms of units, 1.91 additional units of output, okay? Sorry for a so trivial example, but I guess it's useful. So the difference quotient is the number of units the output has changed, divided by the number of units the second input factor has changed, okay? Clear? And the difference quotient is equal to 2.386. This is called difference quotient. We have a two-variable function. It's a partial difference quotient. For Italian, it's a rapporto incrementale. Sometimes it is also called incremental ratio, but it's a rapporto incrementale, but it is partial. What is the derivative? The partial derivative is supposed to measure this, the same quantity, the same idea, when we suppose a very small change, okay, of the second input factor. And as a consequence, we will have a very small change of the output, but the ratio should stabilize to some level, which is the level of the partial derivative, okay, as a limit. When we measure the partial derivative, we have to measure the partial derivative at the initial point, okay, at the point 84. Okay, the partial derivative of this function is 5. It's a Cobb-Douglas function. Partial derivative with respect to y, 5 times x to the power 1/3 times. That was y was square root of y, so the derivative is 1/2 y to the power of -1/2, okay? This is the derivative of the term y to the power of 1/2. Okay? Now, I have to evaluate this partial derivative at the initial point, at the initial input levels, 84. Okay, so 5 times this becomes 2, this is 1/2, and this becomes 1/4y to the power of 1/2. So it becomes 1/2, okay? So this becomes 5/2, 2.5. So the partial derivative, which is supposed to measure, it's a point measure, but this is supposed to measure the trend that you have in your function. If you assume if you want to measure the result of a change, a small change in the amount of one of the two input factors, is basically not too far from the level that you can measure with a discrete change, which is pretty large because it is a 20% change of the second input factor, okay? Also, another thing that you may not, it's so important using approximation is that you may have, in some cases, this is just, you don't need to write it, you may have, in some empirical situation, you may have a function and you have a current level of the independent variables, and you know what happens for small changes around these levels, okay? But you have only a local knowledge of the function, okay? You may not be able to know the whole structure of the function for any values of x and y. You may have only a local change, but you can figure out what happens if you change the variables by only looking at what happens locally, without any global knowledge of the shape of the function. Is that clear? This is a really powerful result, okay? Only local changes. Of course, you must remain near the point, not too large changes. Okay, so this is basically the first partial differential quotient and partial derivative have the same nature. They measure the same effect, basically. One is a point measure, the other is a discrete measure. Now, what is this quantity? Delta y over y. Delta y is the change of the amount of the second input factor. It has changed by 0.8. It was at the initial level 4. It has increased by 20%. What is delta f over f? The initial level of the output was 20. It has increased by 1.91. Okay? So it is 9.545%. Now take the ratio of these two percentage changes. This is an elasticity. This is already an elasticity over a discrete interval. This is called arc elasticity, not point elasticity. If you take the ratio, you get 0.47723. Now, what is the theoretical point elasticity with respect, partial elasticity with respect to y? This is a power function. The elasticity is already displayed here. The elasticity with respect to y, we computed the elasticities before. In general, it's the exponent. It's beta. Okay? So beta is equal to 1/2, 0.5. So the theoretical partial elasticity with respect to y at the initial point is 0.5. Not just at the initial point, at any point. Because this is an isoelastic function. So it has a constant elasticity, okay? So you can try to figure out what happens, try to solve a similar example by assuming, now for instance, that y is fixed at the initial level, 4. Okay, and you assume a change of the first input factor. For instance, a 10% change of the first input factor, which becomes 8.8. Okay, you can try to solve this and compute the same quantities and compare them with their theoretical values that are the partial derivative and the partial elasticity. This is very useful. Of course, you should find a partial, an empirical, let's say, an empirical elasticity over the given interval, which is pretty close to 0, not 0.5, because now it is the elasticity with respect to x, so it's pretty close to 0.33, okay, 1/3. Clear? I think it's useful because you can see a very simple numerical example that confirms what you already know. Okay, so this is just, here I just explained at the end of this exercise why the elasticities are constant, but we already know that, so we don't need to look at this part of the slides. And the next exercise is to approximate, okay, the next part of the exercise is to approximate linearly the value of the output when the two input factors are 8.8 and 4.8, okay, so this is the one we already tried before. This is the one left to you as an exercise. But now approximate linearly the value of the function at the input levels 8.8, 4.8, and approximate this value near the initial input level 8.4, okay? This means that we use basically the tangent plane to the surface at this point. What would be the true value of the new output value? So the first, the initial output level was equal to 20, right? Was here. F of 8.4 is 20. The new output level, I can compute it directly, F of 8.8, 4.8 is 22.616. So what is the output change? It's delta F equal to 2.616. Okay? Now, What is the partial? Now, if I want to compute the linear approximation to the new value of the function, this is like computing the differential, basically, okay? The differential would be the linear approximation to the change. Then I will add the initial level, and I have the linear approximation to the value of the function in the new input level, okay? I have to compute the partial derivative with respect to y at the initial point. We did that already in our exercise. The partial derivative with respect to y is 5 over 2, 2.5. The partial derivative with respect to x at the initial point, I use this alternative formula just to review what we already know. I compute this as alpha divided by x times the initial level of the output, okay? So the initial level of the output was 20. Remember this formula explained before? Okay. The initial level of the output was 20. Alpha is 1/3. X in the denominator 8. Now this is the partial derivative at the new at the initial level of the input. 20 divided by 24, 5 over 6, 0.833. This is the partial derivative with respect to x at the initial input level. So I have the two partial derivatives. I have the two supposed changes of the variables. For the first variable, it's 0.8. For the second, it's 0.8 as well. Okay? I can compute the differential. Then I will add the initial level, 20, and I will have the linear estimate of the new output level. So, the new output level is approximated linearly by the initial output level plus the partial derivative with respect to x times 0.8. I wrote it as 4 over 5, just to have some simplified. Plus the partial derivative with respect to y at the initial input level times, again 0.8, 4 over 5. It becomes 20 plus 2/3 plus 2, 22.667. Okay? So, this is the linear approximation of the output at the new input level. What was the true level of the output? Did we compute it? The true level of the output was 22.616. And here we have 22.667. It's just a linear approximation, okay? It overestimates the new level of the output for the sake for concavity of the production function due to concavity. And the differential, no, not the differential, the linear approximation of the increment, which is basically the differential, is 2.667. Is that clear? I mean, these are very basic examples, but there are, many situations. In principle, if you want to figure out what the direction of the change is, what the approximate size of the change is, you always use linear approximations. In particular, you can capture the direction of the change, whether there is. Here, clearly, there is an increase because I increase the inputs, okay? But in some cases, it's not so clear whether changing the variables produces a final overall increase of the function or decline of the function, okay? But you get a quite precise idea of the direction of the change if you use linear approximations in general, okay? So this is pretty useful. And now, as a final part of the exercise, you can write down the linear approximation to the function. This is just a numerical computation of the approximate change, of the approximate value. Write down the linear approximation to the function near this point. This is a two-variable function which is non-linear. You want to replace this with the equation of a linear function in the two variables x and y, which is more general than just assuming two specific changes. We don't want specific numerical changes. We want x minus, the first change is x minus the initial level, so x minus 8. And the second change is y minus 4, okay? So we are general in this way. Okay, so it's the same structure. My two-variable function is approximated linearly. This means an approximation with a polynomial. In this case, we have the degree 1 polynomial. Is approximated by the value of the function at the initial level, f of 84, this is a number, 20, plus the partial derivative with respect to x at the initial level, 5 over 6, times the change of the first variable. We want to be general here, x minus 8. Keep in mind that this x can be larger than 8, can be smaller than 8. So we can also assume that we decrease the amount of the first input factor, okay? In this case, this quantity would be negative. This is much more general than the previous numerical example. Plus the partial derivative with respect to the second variable times y minus 4, which is the supposed change in the second input factor. So this is the new level of the second input factor, left as a variable. This is the new level of the first input factor. You do the computations and you get, you simplify. For instance, 20 minus 10 here is 10, okay? Minus 20 over 3 is 10 over 3, so this becomes, 10. Minus 20 over 3 becomes 10 over 3, plus 5 over 6x, plus 5 over 2y. This is the equation of a plane. This is similar to the intercept for a straight line. And these are the parts that depend on the two variables linearly. This is a linear function of x and y. Now, of course, if your computations are correct for your plane, you have to obtain the previous results instead of performing the numerical experiment directly, using this general function, which is a plane, and computing the value of the output at the new input levels. If here I put 8.8 and here 4.8, I compute them using the tangent plane, I should obtain the same value as before, which is actually the case here, okay? So, can you see the difference between the previous numerical example and this in which we adopt a more general approach? Here we construct the analytical expression of the whole tangent plane. Then I want to know, we are more general here, I want to know what happens if x and y are two different values from the initial input levels. Just put them into the function and compute the approximated level of the output. While before, we just made an experiment with specific increments of the input factors. Here we are more general. We built the whole expression of the tangent plane at the specific point 8, 4. If we change the tangency point, this means that we compute the approximation at a different point. We don't get the same plane. We get another one, okay? We get a different plane. So when you approximate, in general, when you want to approximate a nonlinear function, part of the solution is identifying a convenient initial point, okay? It depends on the type of application. Depends on the type of application. For instance, clearly in this case, why do we select the initial point 84? Because, for instance, this is the current level of the input factors, okay? We want to approximate what happens if we change them. So we select this initial point as the current situation. Okay? Okay, so this is, I think that's all for today. Well, this is the experiment on the numerical examples on the measures of change for two variables. And next time we say something about concavity and convexity for and variable functions. We will introduce something about matrix notation, and we will deal with more subtle conceptual topics, such as, for instance, implicit function, differentiation rules, and optimization in many variables. Okay, and next time Thursday is holiday. We have only Friday, but all the lessons to be recovered later have already been scheduled, right? So if you look at the timetable, they are already there. Okay, bye. Have a nice weekend. Okay.
Thank you very much.
Thank you, bye.
Bye.
Io sono qua indietro.
Un attimo che voglio solo, aspetti, voglio solo interrompere questo.